Let's talk about touch tones. DTMF, dual tone multi-frequency, or if you're Nortel, digitone. This here is a DTMF decoder IC. This is the ubiquitous, it was ultimately a Mytel design. I don't know who it is now. They've changed hands so many times. But this is basically a Mytel MT8870. It's pretty small. This is another Mytel product. So here, let's, for scale, there's that MT8870. This is on a breakout board that has an audio connection and the clock crystal. This is from my Northern Telecom SG1 PBX, but it's a Mytel produced tone receiver. So all the functionality that's in this thing is in these two anonymous black boxes. They're not even epoxy, they're just lids over circuit boards, and I just haven't bothered ripping them off. Next up is this beauty. This is a Northern Telecom official Digitone brand receiver. This is around the same vintage as the Mytel unit, maybe a bit older. 78, 1980. So 3 thick film doodads here with some Motorola stuff on them. Something very special looking there, which I'm guessing is the magic that makes this work. 160 kilohertz crystal. This is Nortel's version 2 for the SG1. And I will show you version 1. So this is Nortel's earlier version of digitone receiver. This is a bit more visible what's going on here. There's still some mystery components. At least 3/4 of these op-amp looking TO99 packages are Nortel custom parts. So they're QMV1A, QMV1B, and then there's some, I think there's just 741 op-amps. But it's fairly obvious what's going on from this by looking at it. If we count these up, 1, 2, 3, 4, 8, 9, 10, 11, 12, there's 14 pots. Well, for a DTMF receiver you need 7 channels because you've got 4 rows and 3 columns. So 14 pots says that obviously this is 7 channels of decoding, and then there's 1, 2, 3, 4, 5, 6, 7 of those guys as well. So it's fairly clear that this is kind of doing a bit of brute force analog magic to decode each tone individually, and then there's some digital stuff here to figure out which tones are being received and figure out which digit they belong to. So it's kind of neat because it's all out in the open. And then the next thing I have to show you, so here is the American Telecommunications Corporation TonePulse converter. What a creative name. It's a fairly heavy little box of electronics. That's the bracket for mounting on the framework. This is the unobtainium connector used to connect it to between the switch and the line finder. And there's, in this case, this one uses wire wrap jumpers to set which digit to drop out on as the first digit for PBX use. I don't need that for my PBX because it drops out anyway after you dial the first digit. So I've already taken the screws out because nobody wants to watch someone screw on with a screwdriver. Taking that lid off, we get to see what looks like a power supply board, and it is. And then we'll take that cover off, lift this thing up and pull that one off, and there's what's inside. It's surprisingly dense. It's 350 grams of circuitage. It's assembled as a backplane kind of system, so there's a backplane on there with 4 cards crammed in there. The connections on the backplane are interesting. It doesn't use a card edge connector. It uses these little letter M shaped springama things to make contact with the cards. So the only thing keeping the cards in position left to right is this, and this just, I can just take it off just like that. And this is that sticks. These two pieces are just held together with some fiber reinforced tape between them. It's a bit janky. So there it is. The TonePulse converter. 4 boards of magic. Let's pull this first card out. There you can see those connectors. There's not much to them, but they seem to hold up. I've had these cards out numerous times. Let's pull the cards first. We'll call that the analog board because it looks like it's mostly op amps. We have a digital board. It looks like another digital board. That definitely looks like a power supply. And the backplane. So let's start with the power supply. So there's the power supply. From what I could tell, this power supply, well, obviously it takes 48 volts in, and it produces an isolated 5 volt and 12 volt supply, as far as I can tell. I haven't probed it too much. 5 volt for sure, because there's a bunch of TTL logic here. And this is, I'm pretty sure it's a full-on DC-DC converter, because there's transformers and inductors and capacitors, and there's a voltage regulator there. These two transistors appear to be set up in a push-pull kind of dealie, and they're right close to the transformer, so I'm pretty sure this is DC-DC stuff. Also on this board are 3 relays, which are used in controlling the pulsing. Also, there's a couple opto-isolators right there and right there that are part of the polarity detection and loop current detection circuitry. So this board is the one that interfaces to the loop directly. This relay is the one that handles cutting over the line, so whether you're on battery provided by this or battery provided by the PBX, comes from that relay. And then I'm pretty sure that's the polarity switcheroo relay. No, there's not enough contacts. And the pulse, I'm trying to figure out which relay is which. Yep. Lots of Fairchild. That's a Fairchild regulator. Those are Fairchild optos. And lots of RCA. This guy is a CA1458S. That's actually a dual op amp. There's 2 in that package. And they're functionally very similar to the LM741. That's the same. They show up on the same data sheet. I did spend some time with the backplane and tracing out what goes where and which connections are what. That's the analog. And surprisingly, this little power supply module has the most connections and the most tendrils reaching around the system. So it connects to all of the cards. These are the cards have part numbers. This power supply board connects to all of them. This is what I'm trying to get at here. This is interesting. This is the bulk of the tone detector. But as we'll see in a minute, so I've got the TonePulse converter set up on the bench here, ready for vivisection. It's plugged in and working. I've got those 2 points probed up that I talked about earlier, and I'll relocate the camera and show you what I'm seeing on the oscilloscope. It's interesting. So here I've got the scope looking at those 2 outputs on the analog board. I think that's just a bit of power supply noise from the DC-DC converter. It seems to use a fairly low switching frequency, and it manifests as this. You can see it's a capacitor charge-discharge kind of curve. Right. So for the fun part, if I pick up a phone, I should mention I have the 2 channels positioned one above the other. And right now we're triggering off of channel 1, which is the top. So you can see yellow that it's responding to sound, and it seems to be a limited version of whatever the audio is going in. But it's actually more complicated than that. Now if I press 6, which is a good choice, you can see what's going on. Now if I go 6, let me do this. I go 1, 2, 3, you'll notice that top waveform doesn't change. Now if I change my trigger to channel 2, and then I can, oh right, can't do that. So now we're triggering on channel 2. Now if I work across the row, you can see that changing. If I go down the row, you can see them staying the same, or down the column. So it's down the column, and that's across the row. Channel 1, down the column, across the row. So what's going on there? Obviously the tones are being separated into a high group and a low group, and then being presented as a digital output. Why are they doing that, you ask? Well, let me explain. So here we have a here we have a rudimentary schematic of what's going on inside that MT8870 DTMF decoder. How that thing works is you've got your analog signal coming in. It's fed into two filters, a high filter and a low filter. In that there's switched capacitor filters. Then, so out of, you've got your dual tone going in, and then coming out of that, you know, you've got a couple sine waves. And then that goes into a limiter, which just turns that sine wave into a square wave. And then that goes into some digital magic. So what this digital magic is doing is it's looking at the distance between these zero crossings, because these pulses represent zero crossings essentially between them. So if you count these out, so if you've got some kind of time base in here and you count out the number of samples between those, and you see that it's 677 microseconds, sorry, this one 677 microseconds, let's say 677 microseconds between subsequent zero crossings. It would actually be half of that number over 2. And then on this one you're seeing 1290 microseconds divided by 2 per zero crossing. I guess you could, if you measured between positive edges, you could use whatever. You get it. Then you know what tone is being received. So yeah, there's a bunch of digital magic that's got a bunch of counters basically that are triggered by the rising edge of this pulse. So the counter is triggered, and then let's say it's the full cycle. And at the end of the cycle, the counter is stopped. Whichever counter contains a value that would represent a DTMF digit wins, and then you get the 2, you figure out which row and column, which digit, spit it out here, and say, hey, we're okay on that. And that goes high. So that's how the MT8870 works. And what sort of blew my mind is that's also how this is working. So all of this stuff on the analog board, that's doing these first 2 boxes, the filter and the limiter. And then the rest of the stuff is doing the digital magic part and figuring out which digit's being pressed. This isn't what I expected. So my first thought was that it was, you know, doing the oldest Nortel board was doing, which is it has something per channel that's decoding the tones, and so there'd be 7 separate tone decoders. And I started counting up the parts on this, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 22 op amps, because these are dual op amp packages. These are all CA1458S. So there's 22 op amps here, 7 channels. That's 3 op amps per channel, which I think, I'm not an expert on this thing, but it feels low-ish, or barely marginal, and there just doesn't look like enough stuff. And as we saw in that clip, this isn't doing that. This is just doing this. It's doing high group, low group, and limiting. That's it. So the output of this card, which this is not the schematic. This, no. Yeah, this was me working it out. This is when I realized something was going on. So I was chasing out the pins to figure out, because this card has the connector to the outside world, every connection has to go through this card. It has to be exposed here. So the 48 volt supply and the 4 wires of the phone line all have to come in out of this card. So this card picks up the phone line for the audio purposes, everything else it passes through. And I chased everything out, and I realized there weren't enough logic outs. So I had from this whole card, I had 2 outputs that were at a logic level. This is just from chasing the schematic, and 1 logic in. And I thought, oh, that's weird, because I thought this would be decoding to, if it's decoding 12 digits, you need at least 4 binary bits. Well, 2 isn't enough, and I couldn't see them doing some weird polarity-based coding. So that's why I scoped this up and learned that it's doing this. So that means, let's get to the next card. So that's what that's doing. So let's start with this. This contains an interesting mixture of TTL and CMOS logic. This is a 1 megahertz crystal. And then there's a whole bunch of stuff here. So these 4017s, CD 4017s, 2, 3, 4, 5, 6 of those. Those are all counters. The 7493, which that one is a 7493. Oh, there was 2. The 7474s are dual D flip-flops. There's a few of those. 1, 2, 3, 4. Then there's a whole bunch of this MC 14023, the CD 4049, the what's the other one? There are 3 of them on here. Anyway, there's a whole bunch of multi-input gates. So like 3 input AND gates, or one of these is 8 input AND gates. That's these 4049 dudes are 8 input. So it looks like what it's doing is it's got these counters. I don't know how they're structured, but the counters are counting up, and then there's these multi-input AND gates, and I'm guessing there's 7404s in here, 7402. But it's basically has circuitry to compare where the counters are at with fixed numbers that are going to be hardwired into these counters. And so this is doing I'm assuming, based off the fact that it has a whole bunch of counters and large input count basic gates, this is doing the actual counting and figuring out which, and the fact that it has the 1 megahertz crystal tells me that's doing the counting. So that leaves this guy. So on the back of this there are the wire wrap pins, which there's a 7442 here, which is I can't remember if that's a 4 to 10 decoder, multiplexer? No, just decoder. That's wired into those, so that's obviously doing something to check each digit. And then there's just a bunch of, there's more latches and basic gates, 7402, 7400s, another latch, 74, 74, 74, 74. What's a 7490? I looked it up, I can't remember. 7402, 7406, 7400, 7402. So a bunch of glue logic. So nothing too exciting, except, well, there's a 555 here, which I think I know what that's for. And then there's this, which I have tried very hard to find any information on, and I can't find anything. I'm pretty sure that's Fairchild, because there's a lot of Fairchild in here. But I can't find anything. Nothing at all. Not a peep. It doesn't, it's powered off of the 12 volt rail. It's not powered off of the 5 volt rail. It has the same kind of ground and power conventions as regular TTL, which is pin 7 or 8 in this case is ground, and then pin 14 or 16 is power, and that's what this has. So here's my guess, and I'll probably slap this on the logic analyzer one day and figure this out for sure, but my guess is this is the FIFO, first in first out. It's a buffer. When you're dialing, digits are going in one end of this, and this logic is picking the digits out the other end and feeding them into a bit of circuitry that generates the pulses. Which brings me to the 555. I'm pretty sure that 555 is what's generating the pulses. It would seem to me to be the case. We've got the really accurate time base for decoding the frequencies, which is the 1 megahertz crystal over yonder. It wouldn't hurt to use a 555 to generate the dial pulses. There's a bit of plus and minus wiggle room in the ratio, the break ratio, and in the pulsing. So pretty sure that's what's going on here. So this is the actual brains of the system. So we've got, this is just converting the audio signals into something that this can then convert from two frequency-based inputs into 4 binary outputs, I'm assuming. And then we've got this, which takes those binary signals, buffers them up, pulses them out one at a time, using all of this logic. I'm pretty sure, that's my guess. As I spend more time doing this, I'm sure I'll figure it out and probing it. So it's a surprisingly complicated little piece of hardware. So the reason I bought this is because I want one for my system, but I thought, maybe I could make my own. So I actually bought this because I was curious how they did the analog front end, and there's some interesting stuff around how the opto-isolators are connected that I like. It's actually fairly simple. Circuitry to interface with the phone line. So that part I'll probably just lift straight from here. The rest of this is stuff that can be replaced. So this is, a dip is obsolete by today's standards, but those two pieces would replace these 3 boards. So what I'm left with needing is something to decode the DTMF, check. Something to buffer up the digits and pulse them out at the appropriate rate, a microcontroller, check. And then something to power it, which all of this can be replaced with a very compact, modern DC-DC converter module. So really, I could reduce this design to a small board. So it would be this, plus some of the interface stuff and relays, because why not? Let's keep it somewhat old-fashioned. So that's why I bought this, was so I could kind of scope out how someone else did it. And yeah, it's interesting. For the time though, for the era that this was made, 1974, Nortel was busy decoding 7 tones and doing it the hard way. These guys are doing the exact same thing that this thing's doing. These guys are doing some kind of cool signal processing stuff using, as far as I can tell, Jelly Bean logic. And this is all common stuff. Most of the stuff can still be bought new. All the op amps, all of that logic. The only weird thing is this, and I'm fairly certain that's the buffer, the digit buffer, because the high voltage rail, I know my SG1, which uses these are 4x25 stage, so 4-bit by 25 stage shift registers. So these are 100 bits of memory each. It uses these, and these have goofy power requirements. I think they need a 12-volt rail. And it was, for whatever reason, the shift register logic of the day liked a higher voltage rail. So I'm thinking that's what that is. I wish I could have a conclusive answer, but I probably never will. But if I ever get that scoped up on the logic analyzer, it would be really interesting to see what it's doing. I just have to figure out. I might just tack a bunch of 30 gauge wire onto the back. Wish it was socketed. I'm surprised it's not socketed. Probably wouldn't fit. So yeah, very interesting. I'm impressed by the level of engineering that has gone into this converter. There's a lot of stuff going on here in a very small space. Normally I'd be offended by a layout that has packages going in all kinds of directions like that, but they were desperate for space. And I know that because on the analog board there is a 74L74 here, which is, according to my homework, a dual D flip-flop. It looks like one of those flip-flops belongs to this board, but the other flip-flop is wired directly to these pins, so they needed that extra capacity on another board, but they couldn't fit it. So they shoved it on that board and a bit of spare space and wired it through. So it's a very much kind of a tightly engineered package for its era. Like I said, of course these days it can be done in a single die, silicon die. Even my solution is janky and 90s-ish, but whatever. I like things to be maintainable. Oh, one more thing of just interest. Date codes. So it's not as bad on this board. This unit was made in 1974. Do you see the problem yet? This mystery thing. Oh yeah, before anyone says, oh, it's a 7406. No, it's not, because the 7406 is a 14-pin package, and it wouldn't be in a gold ceramic package for sure, because there's a 7406 on here in a plastic package. They're date codes, which they collide beautifully with the 74 series logic part numbers that are all over this thing. That's mostly that stuff. So there's a good example. Is this a 7406 or is it a 7404? Luckily they put the 9N06, which I think was Fairchild's numbering scheme for their Jelly Bean logic. The 74 series was created by TI, so I guess they didn't want to be like TI. So they have this 9N06/7406, which tells me that is a 7406. Yeah, and I thought it was amusing. There's another one. This is a 74122, and it has PCF 7402 on there because it was made in 1974. So it's just this only happened for 1 year, and it was right kind of in the heyday of this stuff. You think they could have picked a better number. And for anyone curious about the unobtainium connector, that's the Amphenol part number on it. And here is a picture of the only data I could find on it from some old catalog. I think I found this on BitSavers. Can't remember. I've checked eBay. I can find this, what is it? It's hard to tell the gender of these things. The receptacle. There's a number of sellers on eBay selling those. There are none selling this little guy, the 223-1509. And there's scoured DigiKey. I can't find anything similar to this connector. So if you have one of these and you don't have the cable, I think there would be no harm in removing that and soldering on a regular D-sub connector, because it's just unobtainium, unfortunately. One more thing, for those of you following along at home, I have taken photographs of each of these 4 boards. I didn't take of the back. I'll do that some other day. But anyway, I've taken photographs of these and uploaded to my website, and I've provided a link in the description so you can play along and take a closer look at these and see what's going on them. If anyone can find me any information on that guy, that would be super cool. Maybe somebody has access to whoever ended up with Fairchild's secret archive of OEM IC numbers.